be offended, never thought they would ever see a big boy run again. How many people thought we weren't going to get it done for May 19th? Put them up there. So we're very, very fortunate. So we got it done on May 19th for one reason. Well, several, but one important reason is the Union Pacific backs this program. And we can't do it without their support. We're very, very fortunate that in the era that we live in, here it is 2020 now. I should say Big Boy 2020, but this is about the rebuild taking place from, when was that? Late 2016, Ted? Right around 2017. So we had planned to start working on this locomotive right when we brought it back. If everybody remembers when that was in 2014. So as a lot of people know the story, I won't get too involved in what we were doing at that point, fixing up the shop and rebuilding the 844 and doing the things that we need to do to bring the steam program and the facility to a point to where we can really do the work we have to do to keep these big locomotives running. So this is a very special picture. This is May 19th, the day that we returned back from our double head journey from Ogden. And I wanted to just identify everyone here on the crew. Kind of hidden, camouflaged up on the engine, and he's with me today, is Ted Schulte. Ted, could you stand for just a quick moment? Ted has been my fireman exclusively since late 2010, and he's just an outstanding craftsman. He's an outstanding fireman. For those of you that don't know Ted, he was a truck driver for many years. He and I built a 15-inch gauge railroad together. He's just very good at everything that he wants to do. He's an absolutely the best machine operator I've ever worked with, whether it's a forklift, whether it's a grinder, whether it's a Dremel tool, it doesn't matter. He's just a tremendous craftsman. So we had planned originally we were going to do things a little bit differently when we went to Ogden with 2 locomotives, and our initial vision was that the 844 would take a trip on its own and kind of celebrate in its own way what the Central Pacific did. Well, as the project went on, there's any number of delays that you'll have, and we had to change the plan and take both locomotives with us. So not only did we have the brand new, just literally put back together again, big boy, but we were going to tuck that 844 in behind it. And I told Ted, I don't know, a week or two out, it wasn't much notice, I said, you and Kurt have to run the 844. And we were all excited about running the big boy. So here, and I'm not sure if we can, let me see if I can tighten up the focus, bear with me just a little bit. That may be all we get there. But we've got a nice bright yellow coat next to Ted is Kurt Clark right here. And Kurt's training as our 3rd engineer, and Kurt is also just a fabulous fireman and a fabulous devoted craftsman in our shop. Will do anything that's asked of him, always smiles, never complains. And that's true for everyone on this crew. In front is Bruce Kirk. Many of you met Bruce. He's been with us in the past to these shows. He's a longtime gunsmith, has a gun store in Fort Collins, and he is one of my ace tool and die makers. So any unique part or any challenge or problem that we have, a really difficult part that you have to work on, something that really you don't want to destroy it, but you have to take it apart, but it's been cemented together with 5 decades of rust, Bruce was the one to work on that. And right behind Bruce is Garland Baker. He's our second half of our brilliant machinist capability in the Cheyenne shop. Garland's responsible for making the precision components on our new CNC equipment. And we've brought some of that here today that we'll talk about when we're done with the main part of the presentation. Garland is one that, so he brings the modern era of computer programming and computer-controlled machining, plus the old world skill of machining, tool and die making. And that's the right combination. Steam locomotives have so many specialized parts that you'll see that to get the locomotive together as quickly as we need to, and also to have the accuracy, having those that machining capability is essential. And he loves that world, and that's the key ingredient with any tight-knit, very specialized organization, is there must be passion. Without it, it's a job. You can't really endure the difficult challenges that you will always face if you don't like it. So we're very fortunate that we've got this team of people. Here's Troy Plagg. He's an outstanding electrician. Troy came from the North Platte Diesel Shop, and he painstakingly hand-built the cab signal control system that we have in both locomotives, but particularly the big boy. And he's just an outstanding electrician, and he fits in with the work that we do in the shop. And then we've got Jimmy Thompson, always smiling. I apologize that this picture does not show his beautiful smile, but I'd also like Jimmy to stand up. He's with us here today too. So as we were going through this really difficult time, you know, I never served in combat, but I did serve in the military, and we trained for combat a lot, as you do when you're 18, 19, and 20 years old. It's during the Reagan military buildup during the Cold War, and I was one of these guys that thought the Soviet Union was going to invade us, and we were going to have to deal with them. They sent me over to Europe, and we went through some really neat training, and that training taught me a lot about things, pressure, stress, and that you can do anything that you put your mind to. Well, that came in really handy when we started working 7 days a week, 15-hour days, and you know, there's pressure on you. You know, that's life, right? So we came up with a neat little way. I like having fun, and we like to have fun in the shops. And I started to draw military insignia on the lapels of our green welding coats. And we all kind of wear these coats, and they're designed they're almost disposable, but if you take care of them, they'll last for a couple of months. So Jimmy quickly was promoted to sergeant, and that's his nickname is Sarnt. So we referred to each other that way. Ted, he didn't get too much into the ranks, but Ted was a warrant officer, so was Kurt. Austin was a sergeant major. I was a major. Bruce was his gunner's mate with his Navy ranks, and we had fun with that. So if you hear me call him Sarnt, that's what that means. And next to Sarnt is Don Creer. He's the other part of the boiler-making talent that we have. The welding skill that Donnie and Jimmy bring is what you would expect when you're going to weld together a 1941 steam locomotive boiler and expect it to be as perfect as you can make something that is old as it is. And that's kind of what we're going to get into. We're going to get into why we do this, and we tear something apart. And you can't be too nostalgic about old parts, because if the old part isn't going to work, you got to get it out of there. And that's what Donnie does. And here's Austin Barker. He's a foreman general, and he is, like all of us on the crew, he was born for this. This is his life's ambition, as it is mine and all of ours on this crew. Austin lives and breathes this stuff, and that's the key ingredient too. I'm not too embarrassed to admit this in a group of railfan people, but I like trains. And so does Austin, so does Ted, Jimmy, every one of us, we like this stuff. And so we're lucky that we've got this opportunity to work on railroad equipment. And then this is me standing up here. I've got my red bandana. That was a special bandana given to me by a good friend, a manager in Evanston. and he's a cowboy out west, and it's just an outstanding individual, and he partnered up with us and helped me behind the scenes with operating details, and he was present in the cab with us when we brought the locomotive together with the 844 at that really iconic moment when Lance Fritz called the 4014 and told us to bring it ahead. So just before, right after we got this picture done, we were just putting everything away, putting everything into the shop, and we're going to take a little bit of time off. Prior to that, we really hadn't had opportunities to take time off because of the mission that lied ahead of us. Another shot, and this was taken just after we got the 844 back in service. And again, we've got Ted and Troy, myself, Jimmy with the smile, Donnie, Garland, Austin, Dean, our fuel truck driver, and Bruce. And not pictured here is Kurt Clark. And this is our wonderful, one of our colleagues from Omaha, Kristen South, Director of Corporate Relations, Media Relations. And I really enjoyed this because she was out in the shop. We had Trains Magazine out at a period of time during the rebuild. And just look at that smile on her face. And she's enthusiastic. So we got inside the firebox, inside the big boy, and we did just a little bit of a video clip that we could release to social media. But this is an example of the cohesion, the teamwork that we have with our colleagues in Omaha. And we can't do any of this without them. So it's not just a group of people out in Cheyenne tinkering around with old stuff. There's a lot of folks at the headquarters building, thousands and thousands of them, that deserve all the credit for getting this locomotive together. And she's got some young children that were so excited that mommy was in the big boy. So I think she texted them a picture not long after I took this picture of her. And a quick shot of the 844, and this is what the big boy looks like today. So a new cab floor, and we made a lot of new parts on that. And it's really interesting how things just work out for the good. And that is that going into the 844 project, we realized just how deficient the shop was in terms of usable resources, tooling, equipment, basic necessities, things of that nature. So that allowed us to really get our head around what we needed to do to fully jump into the 4014 project. So let's do that. So here's the big overhead crane, and it's a 40-ton crane, which is nowhere near as big as the crane that you need if you're going to completely rebuild locomotives day in and day out. But it's just what the doctor ordered for what we need in that shop. So if you can see up here, all of this was behind an office-type ceiling, if you can envision an area here. So all of this artificial, or excuse me, the natural lighting was blanked off by a ceiling kind of like this one. And that ceiling requires a pretty comprehensive metal frame grid to hold those acoustic tiles in position. So there was quite a lot of infrastructure up above that just so that ceiling could be there. And there was some lighting and conduits and stuff kind of haphazardly strung through all that network of gridding. So we needed to strip all that stuff out of there, and it reveals the shop in its 1919 glory. Well, it's pretty dirty with all the birds and everything that were living up there, but this is one of the main reasons that we did that, so we could put this crane back up here. So in order to make that work, you've got to do a lot of engineering analysis and assess the structure of the building to make sure that it's still sound. You know, it's been there 100 years last year. So we did all that engineering work, and the good news is, obviously, the building's in really good shape. So we put that thing right up in there, and we put it on the upper level. So that's 48 feet over the shop floor right here. And this crane is actually hoisting the trolley that is going to be positioned up here that will traverse along these big giant beams. And then that, of course, traverses the full width of the shop. So that is really a very important tool, as you'll see. And then a quick picture to pay tribute to all the work that it took to bring the locomotive back. And I try to take a lot of pictures. Austin takes a lot. I encourage others to take as many as we can. And this was one of those random pictures where we're very busy. We just moved the locomotive back, and now we got to disassemble all the track. And I snapped this picture right at the moment where Austin was turning and looking at the locomotive. And we talk all the time about the memories that we have and all the things that we've done. And you just wonder what we're thinking in the moment that picture captures that. And speaking of which, look at the determined look on Bruce as he's dragging some chains and some heavy equipment, and everybody's working. We just got through taking the front engine out of the big boy. And in order to do that, we need to strip it down and make it light enough so we can lift it with the big 70-ton hook side booms that we used. Hi, Rick. So we made what we call a dolly truck to support this and all the various other things that we need to make this happen. It was pretty cold that day. As planning goes, we didn't plan to do this when it was dark. But once you get started, you've got to continue on. There was a pretty good snowstorm. Something like this takes weeks of planning, and you get on the calendar of a company that has this capability, and as luck would have it, they got called away to a derailment and were delayed. So they didn't arrive in Cheyenne until later in the afternoon. And we're going to go ahead and we're going to carry on. And here comes the snow, here comes the cold. But we got it done. So that's what the front engine looks like right when it comes out. And this, it's no exaggeration. This is what the 844 is, with the exception of a smaller diameter wheel, and the cylinders are just a little bit smaller, not much. So that gives you the sense of scale of how big a big boy is. It's a massive machine. So as you're taking the locomotive apart, you kind of forget. You kind of get focused on all the other things that you're doing, and you forget that it's a big locomotive. I know that kind of sounds a little bit strange to put it that way, but I'm going to come back to that comment. I want you to remember that. So we disassembled everything. We've got all the lubrication lines, all the piping. We've stripped this thing down to almost every piece that we can physically remove. And now we're going to take it outside. We're going to build ourselves a little area, and we're going to sandblast this thing down to bare metal. You've got to do that. You would spend probably a year if you tried to needle scale or wire wheel or something like this. You get a big industrial bead blaster, and you go after it with some really aggressive aggregate. It kind of resembles miniature railroad ballast. I mean, this stuff is really, really abrasive. And it's called Black Beauty is the name of it. And it resembles pumice. And it goes through with 100 plus PSI through a nozzle. And you have to wear a full protective gear with a supplied air respirator. But you cannot even be within 20, 30 yards of that thing, that abrasive ricocheting off of that. I mean, it hits you, you don't want to be anywhere near it, trust me. Disassembling the inside of the boiler, getting all the superheater units out, the stack extensions. We're replacing all of this stuff, so you torch that. And you get into the locomotive and you judiciously use a cutting torch because there's pieces that we don't know if we're going to replace them. We want to, but we have to be mindful of the fact that as the project progresses, there's a chance we won't be able to get to that point. So you just don't want to demolish everything. But you've got to pull that stuff out of there. And this is a Type B superheater. So for the steam locomotive people in the room that understand a Type B versus a Type B is the more complicated version. It does provide a greater degree of superheat, not that that matters, but back in the days when you were selling locomotives, that was a selling point. The second series 4000s were built with a Type A superheater. and namely because it's easier to maintain, and overall it's a little bit easier, as if anybody that's worked on a Type A can attest, or excuse me, a Type B. This is a shot of Bruce Kirk holding some of the custom tooling that he made. And a tool and die maker, a machinist, any fabricator takes his time to make tooling. You can't rush through that process. And what these two components do, initially we made only this cutter, and it's known as a sleeve seat cutting tool. And these are brand new staple sleeve caps. And inside, before, you can see here that there's a little bit of a yellow area. For some reason, that gasket seating surface is not at the right relationship to the axis of the staple or the axis of the thread. So when you screw that on there, that it can leak. So we made this seat cutter. Well, the problem that you have is that the corrosion and the rust is pretty darn tough stuff. And it dulls your cutter. So you might use the cutter once or twice, and you've got to take it apart and resharpen it, and it just takes a long time. Well, don't worry, Bruce has got it figured out. He's going to devise and custom make an abrasive stone. And that stone, so it's a two-step process. You screw that tool on there, and it's got like a crank handle, like a jack-in-a-box crank handle. Dun-dun, 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 dun-dun. And he runs that handle around there, and that takes that corrosion off that really hard scale layer. And then he can take that off and put the cutter on there, and that cutter removes the material, because you have to physically actually cut the material down. You've got to remove material. You can't sandpaper it down. You've got to physically cut it down. And that's what he does. The bluing on there, that's what we call that, and that's used to determine how much material. Hello, Marlon. It's good to see my good friends down here. Now this is some piping, and think about all the different airlines, steam, water, lube, different types of oil, engine oil, valve oil, grease, air signal, brake pipe, equalizing reservoir, brake cylinder, air pump exhaust, live steam air pump, governor airline. Think of all these airlines that run from the cab to the front of the engine, from the front engine to the rear engine. Well, how does all that stuff get down in there? And on an articulated locomotive, as well designed as these locomotives were, it's like a big giant puzzle project for draftsmen. They're figuring out how to route all of this stuff down in there. And it is an absolute work of art. So we take it apart, and we've got this old, rusty work of art that we're going to duplicate. So throughout the project, we invested in a lot of tooling and a lot of equipment, and we bought two different pipe benders. For those of you that have worked on steam locomotives, it's pretty tough bending pipe with an acetylene torch. You know, imagine bending all this with an acetylene torch. Well, this was done in literally a matter of minutes with special gauges, tools, digital levels that you can put on there, and you can custom tweak and fit each one of these bends. And Austin, as he is with everything, figures it out in about 5 minutes, and you just stand back and watch the production. And we've got another little piece that is welded to this pipe here. Some more really neat, cool parts. These are valve stems out of the turret valve. And you can see, oftentimes this is a result of many years of use, but sometimes it's sitting in water that does not have the proper water chemistry, or it's just a component that just sat around a long time. A lot of this can happen when you let your steam locomotive sit around wet and cold all winter. You don't want to do that. You want to lay your equipment up. So here's the new part right here. More new parts. These are throttle valves. And excuse me for getting in your way here. Just to show just how big this equipment is. This is a firing valve, and that's in the front there. That's a beautiful new casting right here. And these are all throttle valves with new balancing pistons in the stirrups. And these are forged. Very, very, there are so many parts on a locomotive that are critical. It's hard for me to think of any more critical component than a throttle valve, because that's what's containing that 7,000 horsepower, over 100,000 pounds of steam per hour capacity on the big boy boiler, and it's being held within the pressure vessel by those 7 valves right there. So we needed to replace all of them. They were just too worn out. So it took a little bit of work to get to find a company that could forge those for us, but we succeeded, and they provided great 8630 modified vanadium alloy steel forgings for us that Garland machined on our beautiful CNC equipment. More views. This is a continuous blowdown. A lot of people have questions about the operation of the locomotive, the 844, the Challenger, the big boy. We rebuilt and put back in service the continuous blowdown system that was not in operation for decades, and we put it back in service on the 844, and we've got 2 of them on the big boy. And there's really no mystery behind the concept. You're simply releasing water out of the boiler, and it's known as a continuous blowdown. And the original design involved a piston that was controlled by exhaust steam pressure, and so that simply means when the throttle is open, the engine is working, and the live steam does its work, and then it's exhausted up the stack, and it's not used anymore. But that exhaust pressure is used in this instance to activate that piston, which simply pushes a ball, a stainless steel ball. And let me see if we got a picture of that. You can't even tell it's a stainless. There it is right there. It looks like a blob, but that at one time was a stainless steel ball. And it pushes the ball off of a seat, which is right down inside here, and therefore it releases and it starts that flow of water out of the boiler. And all you're doing, if you can think about a big giant pot of water on your stove and you boil it down to nothing and you have residue that's left in there. Imagine the cycle of a locomotive operating down the track, and it's producing tremendous power. And that power is what we call evaporative rate, the rate at which it's consuming the water. Well, that water, as it's evaporated, as it's being used, is essentially pure, beautifully clean, nice water. Well, what a shame, it's going to be wasted. And everything that was in it, guess where it stays? It stays in the boiler. And those concentration levels continue to elevate, and they get to unmanageable levels, which cause any number of problems in your locomotive. It will get to the point to where you can't use the locomotive anymore. You're just boiling a pot of mud, essentially. Well, the continuous blowdown theory, that coupled with the judicious use of regular blowdowns, helps release or control those levels just by diluting them out of the system. So that's what you're seeing when that big boy's operating. You're seeing, and you can run the numbers on it, you can take the numbers of your water analysis depending on where you're going to go, and you can calculate the water softener and how many grains of hardness and how much sodium and all the TDS and everything, and you can kind of get your head around how much water per mile you have to get rid of to maintain your levels at the end of the day where you want them to be. So it's a neat science project. It's something that I'm interested in, and we've got, for those of you that know Paul Gershio, he's a wonderful chemical engineer. He spent his career with ExxonMobil. He's a master's degree Notre Dame chemist, and he likes it too. So we're kind of the chemistry geeks. But it's something you got to do. And that's one of the big problems and one of the reasons why you saw dieselization occur rapidly after World War II. Railroads were looking for a better solution, and this was a big reason why. A stay-bolt. This is a CAD drawing of our Type KJ stay-bolt. I brought an example of those today, and there's thousands and thousands of these. This is a rigid stay-bolt here. This particular one, or excuse me, a flexible stay-bolt. But the material is the same. The method of manufacture is a little bit different. It has what's known as a telltale hole, this right here. This little hollow cavity extends up into the spherical ball, and that simply tells you when it's cracked or when it fails. And when it starts blowing steam out of the hole here, and we've got a little sample over here that you can come look at when we're done, that illustrates how that whole system works. Pretty fail-safe, tried and true, old technology. And this is what the stay bolt looks like when you're all done. So there's many steps in the process, and I'm glad Jimmy is here because I want to talk about just what it takes to work on a locomotive firebox. It's just an unimaginable amount of work when you think about how many stay bolts are in these things. So when you go through and you're assessing the boiler, and keeping in mind that this thing's going to bear 300 pounds of pressure, 7,000 horsepower, and it's portable, it's mobile, it's rolling down a rough track structure. So this thing is really heavy duty. In order to maintain that heavy duty, you've got to make sure all your stay bolts are good. So this material is low carbon, and it's formed with hand tools and pneumatic equipment. And you're forming that by hand. So all the small little striations you're seeing here is the hundreds and hundreds of hammer impacts per minute. Just striking that, and you're holding the tool with your hand. And then when you're done, we have a drill and we reestablish the telltale hole because this material is so soft, and that's what's important. It's easy to think about a boiler and think, well, why don't we just make these bolts really super heavy duty? Why don't we go to the store and buy some really heavy-duty bolt material and then they don't break anymore? But understanding how a locomotive works, it's designed to be flexible. So you've got hot and cold, you've got heat, you've got the pressure from when the locomotive is cold to when it's in full operating condition. When it's operating, there's variations on the demand of the boiler. When it's going down the track producing 7,000 horsepower, that horsepower is transmitting through heat through the metal plates that these stay bolts are holding. So you're going to have those variations. That's why it's so important, and that's why Ted is so good as a fireman, because he keeps that pressure at 300 pounds 24/7. Well, not 24/7, but you know what I mean. When we're going down the track, keeps the smoke down, keeps the heat up, and what that does is keep our expansion and contraction to a minimum, which extends the life of this component here. So that's all formed by hand, and it's all smooth. You can see the small little lip around the edge. We call that caulking, and that's the final step. So you form this thing by hand, and then you take a separate tool, so it's a multi-step process, and you hold that in your hand, and you develop some pretty good arm and hand strength. And you're forming that as you're forming that tool around to make that shape. I think maybe 5 or 6 minutes. Jimmy, do you remember?
It takes it's about an average, if you had to do one bolt, all the steps from beginning to cut it out to put it back in, it takes about a day, 8 hours.
Yeah, an 8-hour shift for one, doing all steps. So if you're going to clean up the threads, you're going to machine the threads out, you're going to weld up the hole, reestablish the hole, penetrate the hole, ream, thread, install, form, seal, weld, the whole 9 yards. That's an 8-hour job. So when you're doing a whole side sheet, or you're doing a whole, as you'll see, an entire section of the boiler, we do all those steps one at a time. So each one of those steps, it's just a sequence. And we get into a process and get into a rhythm, and they're all identical. And we want them all to be, I use the word perfect. That's a good way to think about it, because when you've got thousands of these, or in the case you're going to do hundreds and hundreds of them, it's easy to kind of start shortcutting. Yeah, it's good enough. You're so tired, you're so fatigued, you just want to be finished. But you've got to get through it and do each one of them just like the first one you started when you were fresh and it was 8 o'clock in the morning. This is the seal weld, and this is what we do on the inside, and we haven't drilled that out yet there, but the seal weld ties the two metals together. So You caulk the outside, but you seal weld the inside. So as that tremendous 7,000 horsepower, 2,000 degree flame is burning inside that firebox, that heat is transferring through the steel. Well, this is a little bit thicker than the area here. Well, we don't want that heat to start building up, so we have to give it a pathway to transmit that heat through the rest of the material, and that's what the seal weld does. The seal weld ties in the two metals physically, it melts them together, and then that eliminates any risk of that starting to separate through the heating effect of that. So that's part of the science and the understanding of what's going on inside that boiler. The Union Pacific, all big railroads did lots of testing over the years to determine the best practices. And this is a Union Pacific practice. Southern Pacific, Great Northern, New York Central, Pincy. Other railroads had different practices. Some of them didn't seal weld, some of them did. Some of them used different tools. Some of them didn't use telltale holes until they were mandated. It's just a matter of personal preference and what the railroad philosophy was. UP has always evaluated everything from an economic standpoint, and they needed to extend the life of the boiler and the firebox, and that's what drove this practice here. And there's some more. This is the outside of the boiler. This is a new machine seat for one of the blowdown valves. These big heavy-duty studs, all new material. You can see all this nice new material here. And that's one of the blowdowns, all rebuilt, real nice. And this is the big boy firebox with the tube sheet cut out. And we replaced 2 rows of staples, which was pretty common when they did, on the big boys, typically put a new tube sheet in this thing every year. That's how much, they were very serious about boiler work. But when you're pumping 28 tons of coal through this thing in 4 or 5 or 6 hours, you're going to wear some stuff out, and you're going to need a new tube sheet. So we did the same thing. We just cut it out of there. And now you're actually standing in the middle of the boiler, looking back toward the cab. You can see the circulators here, and there's the fire door right there. And here's the plate that we're going to form and fit and start to put in to replace these sections that we have to fix. And this is big heavy duty fabrication. So we've made this section of the mud ring and we formed it in our press brake very accurately to fit. Now this is after days and days of Jimmy and Donnie welding up the mud ring. Welding up the holes, welding up the actual exterior surface of the mud ring, making it so it's where it needs to be. So when we go to fit this up, it's going to mate with the rest of the sheet that we're going to put in there. So we bought some really nice tooling, and a lot of this tooling is made for the power plant industry when they go through and they take a big coal-fired, or any power plant for that matter. They go in there and they have to rebuild that power plant, and they've got hundreds of guys that will come in, men and women will come in there and just dig into the thing and tear it apart and rebuild it. So we bought some of the custom tooling and had them make us some very custom tooling that we could use to countersink these holes. So we're machining all of the rivet fits on this piece here. And here's this piece here, that's Jimmy, trying to move out of the way of the camera. But here's a section of the firebox that we replaced. And you can see all of those staples. And here's a whole bunch of other staples that we replaced. You just get in there and just start tearing into it. And here's the new tube sheet that we put in there. But that's a real big patch down in there. Now this, and I apologize that the audio is going to be really poor, but forgive me, I'm going to try to be a geek and hold my microphone over there. This is a video sequence taken in slow motion of us driving the rivets. And I'll play it for you. So you're holding this gun, this rivet gun, with a rivet snap, and each one of those impacts is a piston driving into that tool, which is forming this 1800-degree hot rivet. This is what it looks like when you're done. So you're holding this by hand. Ted is sitting behind me holding on to me because it pushes you back, and you have to sit, and we build a platform in there, and you can't hold yourself because you have to use both hands, and you're sitting on a pad. So Ted is hugging me and holding on to me, and then somebody holding on to him, and we've got two guys on the outside doing the same thing. And so there's what's called a manufactured head, and this is the formed head. So we're forming that rivet, and I'll just kind of turn it on so you can see. So we form these countersink rivets, and each one of these is called a fit bolt. So we fit those in there, and that holds the sheet in the final position. So we fit those up. And there's a few different ways you can do it. You can do it without welding. You can do it before when you're done welding. And we welded this, and then we put the rivets in. And this is a portion where we're forming part of the exterior elephant ear patch. So we very accurately we took a scan, and it's really neat with the technology today. We had a 3D scan of this particular part of the boiler so we could form this plate, and we drew in CAD each one of these individual plates and then welded them together to make a male and a female die. And we put this in our 100-ton press, and then we made an oven that could heat the plate up to 1900 degrees. And then we, by hand, this is a very large plate. It's about the size right here. And it's heavy. And we pull that thing out of the oven. We've got this oven made on this table. And we've got it all made with brick, and we've got all kinds of propane torches in there, and we're trying to heat this thing up, and it takes well over an hour to get this plate hot enough to form. And that's how we formed those particular patches, because they've got to fit on that part of the boiler. On these particular classes of engines, it was a slight design, I don't want to call it a flaw, but they needed to be reinforced. So we took those reinforcing patches off, because when we did the inside work, we could see some problems with some of the welds. So we took them completely off of there, fixed the issue with the weld, made new patches, welded them all back up. And this is what it looks like here. You can see that patch right there. So we've extended it, we made it actually bigger. And there's Ted down there working on some lubricator lines. But in all the rush and all the busyness, I didn't take pictures of that plate when we put it on there. So this is the only one I had. Now we're getting into some more machinery here. I tell you what, let me see here. I wanted to kind of take a break here in a little bit if everybody was interested in that, and maybe everybody could get up and stretch and go get something to drink or something if you'd like. And I don't want to put everyone to sleep. So here in about 5 minutes, we'll take a quick break. So these are the eccentric links and link trunnions, and these are all forged components, just like the throttle valves, and all machined, just beautiful representations of what they would have done in the 1940s when they made the locomotive new, and when the Union Pacific shopped them many times. So the running surfaces for the valve gear, these are pretty worn. These are brand new. So like everything, it's on the list of things we're going to make new. The trunnions bolt on here, as you can see, and that's what actually holds and operates the link. Now we're back on the cab floor. We've got everything, starting to put everything back together again. And we've got a new deck and the air brake pedestal mounted and starting to fit everything up. And we've got this access plate, which we made, just like on the 844, we made that out of stainless steel TIG welded. So it can be removed and allow us to take that drawbar pin out from the cab end rather than having to drop it from down below. It gives us access to the fuel lines, gives us access to air brakes, just another way in. Once you get the locomotive put together, it's hard to get down in there because there's so much stuff in the way. So if you really need to get down in there and you've got a problem with something or something's leaking, this is one way you can get in there. This is what it looks like starting to come together. Beautiful wood, nice oak floor, the reverse gear coming together, the new oil firing manifold up here, rebuilt cab, just a beautiful machine. And that is just a little bit farther along the line. Now this is one of the projects that just kind of illustrates what you do when you're rebuilding something. This is an expansion joint for the live steam line that runs to the exhaust steam injector. That's one of the ways that you put water in the locomotive. And it's MIG welded bronze. So for those welders in here, that stands for metal inert gas, MIG welding. It's a really fast way to put on metal. And so it's welded on there. And then it's machined down in a lathe. And over the lifespan of this locomotive, it'd get taken apart time and time again, and every now and then you might nick it with some torches. So you just weld up all these little areas. And then when you're done, you chuck it up in the lathe, and you machine everything down, and it looks real nice, looks real pretty. And then you make all the other little pieces. Garland made this packing gland. It fits down in there. I'll show you what that looks like. And that's what it looks like when you're all done. The locomotive is so long, this run of pipe is close to 65, 70 feet. And the locomotive being so long, it does grow. And when this operates, the pipe itself, from cool to hot, moves this packing gland every single time it operates. As a matter of fact, on the trip when we first left heading to Chicago, I wrapped a rag around that because it was starting to get rough. And I just would pour some valve oil up on there. And the rag, you couldn't really see it, but there's this rag wrapped up in there, and you boil on it every now and then. Well, Ted just got through putting a lube line. So we've got a force feed valve oil lube line that goes to that to lubricate it because it moves so much. And that'll make it last a little bit longer. So that's the expansion joint. And now we're going to put the spring rigging in this big monster. All of those springs are so big and heavy, you cannot lift them enough. You can't pick them up. You can't manipulate them with one person safely. So we've got our overhead crane holding this, the 5-ton hook holding this big number 623 driver spring, and we've got a chain hoist and we're pulling it in on the side here. Putting drivers in, more spring rigging. This is a brand new casting. It does not do justice to how big it is. That's called an equalizer over driver. So under the firebox, you can't have the suspension system that the rest of the locomotive have because those two drivers are underneath that front part of the firebox. So all of the suspensions, all of the mechanism that transfers the weight to those drivers has to be very low profile. This is design that goes back to the early articulateds, the Moffett Malleys, all the early articulateds had this same style, Pacifics, 10-wheelers. A lot of the engines with drivers under the firebox have the equalizer over driver theory. We made these brand new. We started to weld on the old ones and they just were too wore out. So we just made new castings. But all these big driver springs in here, all the complexity of this locomotive is hidden. So much of it. All of the really hard work, you can't really see it. When you think about what it takes to put a big locomotive together, I'm not going to oversimplify it by saying it looks easy, but you have no idea how much stuff is inside this thing. All of the frame pedestal bolts were replaced. We were running out of time. And we were going to just make the ones that were really bad new. Well, by the time you mess around with chasing the threads on that thing, you're just better off. And we made all new ones anyway, so we got down in there and we went to town. It's fun working on this stuff. You're down in the pit, so you lower it. I'm 6'2", so you're standing down here using what we call a rivet buster, which is a really big tool. As the name implies, it's designed to drive out rivets. And you take the nut and you weld the nut on the old end of the bolt, because it's junk anyway, and you get down there and you hold this rivet buster and you prop it up on your knee and you and you start pounding up on it, and everybody in the shop can hear it because it goes plank and it falls down. Except it's a lot louder than that. Crash! Boom! And then you clean up the hole, you clean it all out. If it needs to be welded, I'll go get Jimmy, take him off of whatever he's doing, or Donnie, and away we go. And one after another, you make this stuff brand new. And brand new it is. This is a new casting. This is a new casting. These are new bushings that will go into new holes. Brand new springs, welded up, all beautifully painted. And this is known as a gag. And this is a metal framework that you create around the spring pack, and you have to put that stuff together inside the press and compress those springs. And it's dangerous because those springs are designed to carry tons and tons of weight. And they won't fit in there, and they're decompressed in their free, what we call the free height. They won't fit in there. So you've got to gag this pack. Well, that's a little unnerving when you've got a 100-ton press and you're forcing this stuff down, and you make all these pieces of 3/8 bar stock, and 3/8 ended up not being enough. And you can see it bending. And you've got it welded here, and you've got it welded here. Well, one of them actually broke. And I welded it, so Austin really gave me a hard time about that. But it just ripped the metal right apart. So we went with a little bit bigger material and made it so it would hold in there. But it's really exciting when you go to cut those. Once you get it all into place and you block it up and put it all together, and it can move around because those springs are tightly compressed in there, then you get in there with a torch. And you're sitting there and you cut through it, boom, and that thing breaks. And you got to fish all those metal parts out of there. And there's a picture of Garland making our crosshead guides and fitting those two halves together. This project in itself is just many months of work. Lots of coordination, fitting all of these very accurate fit bolts down inside those two halves of that crosshead guide. Very accurate component. That manages the thrust. That takes the full thrust of each piston. There's 4 of those, and we made every one of them brand new. Each one of them is in 2 halves, all brand new everything, and fit up on the side of the locomotive. And this is what Garland does. There's Jimmy and Ted working on lube lines. Jimmy and Ted, we work together in work groups often. Sometimes we joke about, we've got a couple of the guys, I'm not going to mention by name, we call them the besties. Every now and then we got to split them up. They're over there, they're not goofing around at all, but we joke with them. All right, we're going to split you guys up. Remember that, Ted? Well, here's the besties, Ted and Jimmy. We don't have to split them up. But they're working on new lube lines. Ted did most of the lube lines on the rear engine, correct?
Yeah, Austin did the front engine.
Yeah, beautiful workmanship. When we travel with the locomotive, I've tried to figure out how in the world could we put a mirror underneath so people could see what it looks like under there, because it's just a work of art. It's like a finely restored automobile. Here we are inside the boiler just before we put all the tubes and flues in, and this just shows the remarkable condition of the inside of the barrel of the boiler. Once it is completely cleaned, and we paint it with a special coating of paint known as epoxy, and it's a specific type of paint designed for the inside of a locomotive boiler. If properly applied, it'll last for years. These are tube sheet braces. We removed a few of them in order for us to do a little bit more work. Did we shorten? I think we shortened these. I know we did on the 844. It's starting to blur together for me. So this is the tube sheet that I mentioned here, and these are the radial stay bolts that we replaced. So we replaced 2 rows in. You can see where this formed plate here forms over and becomes part of the crown sheet, and these connections are threaded and then seal welded as I described before. The term radial stay is really evident in this view. They radiate outward from a center line of the boiler out to the wrapper sheet, and each one of these is withstanding the tremendous force that's being exerted on that flat plate. And these are the front tube sheet braces. You can see how symmetrical everything looks, and these big heavy-duty castings. So the steam locomotive is something that's designed to last a long time. And so these are known as brace feet, and they're riveted to the unstayed surface. Once they're riveted and attached here, that stays or holds the very front part of the top of the front tube sheet. Just to the left here is the dry pipe that penetrates that, and that's connected to the front end throttle and superheater header. So all of the steam pressure that's being contained in the pressure vessel is being held by each one of these components. Each one of those is designed to withstand a tremendous holding force. All of them together work in unison in a very precise engineered design to hold everything together. So steam locomotives were built this way with a very significant safety design factor depending on what component you're talking about. And that's what's important when we go in to assess this stuff, looking at it and trying to figure out exactly what needs to be repaired and how we're going to repair it. So we go back and we make it the way that they used to. We do it the way they did. So these are brace feet pins, and they're held together with a threaded nut and then a cotter pin. So you want to make sure that those cotter pins are in there naturally, stainless steel, so they don't just dissolve away into nothing. And each one of those is doing its job. Each one of those is tight. That's one of the inspections you do. You roll along in there and you're doom, 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 doom. Each one of those has a specific tightness, and you can tell when they're loose. A few years ago when we worked on the 844, we actually took 2 of those big long braces out. They were not tight, they were physically loose. So we shortened them up a little bit, got them tight again. And this is the top check of the front part of the boiler, and some of the big framework that holds the sand domes. The sand domes hold thousands of pounds of traction sand, and they also fit around different components up there. So in order to get into that top check, unlike the 844 when it's sitting right out in the open, you've got some doors up there that you can work down into. And these are all new, just beautiful. We rebuilt the castings, but the spindles and the stems are all new. And this is what it looks like as it's coming together. All the beautiful pipe work and piping, all the stay bolt caps. You can see all the new ones that we put on there, and all the various different runs of piping that does specific things, power reverse, bell. Now we're inside the firebox on the oil conversion, and that's something that's really been interesting for a lot of people. And the oil conversion in itself there's nothing mysterious about it. It's just quite simple. We employed the same system that the 844 uses, a system that was developed in and around the time, probably right after when they had the oil conversion on the 4005. So if they wanted to convert these locomotives and they needed them to be oil burners, this is probably what they would have done. They had a little bit of a different design in on the 4005. They removed the circulators and did a few other things on that. So we just took that engineering a little bit further, and this essentially is what the 844 has in there. And this is one of the fun things that I get to do. So we fabricate this fire pan inside there, and there's your burner. It just has one single burner, and all the circulators are in. And then you hand place each one of these bricks, and you literally build yourself all the refractory inside. We welded a framework in around our air tubes, and you simply calculate the flow of gas through the surface area on the tube sheet, and that gives you a really good idea on what percentage you need at what location. And that's what you've got here. You've got the air inlets on the side, and they're angled such so you've got air tubes moving upward, and you've got some that are down at the floor, and then you've got another. Let me go down here a little bit more. I don't know if I've got it. But you've got air that flows in the side, and so this is a demand system. So there's nothing causing the air to go in there other than the exhaust pressure created by the exhaust in the front end working through the nozzles that I've got over here. So it's a very simple system. Steam locomotives are very simple, and you've got to remember, if you introduce complexity, it's got to pay for itself. And if it doesn't pay for itself, it's got to go. And that's what the steam locomotive is. Everything on the big boy pays the bills. It's not there to be pretty. It's not there because somebody thought it was cool looking. If it doesn't work, it never made it past the 1930s. So that's what this stuff is here. And we've got these little bullhorns welded on here. We have a special refractory available to us today. We call it plastic, and it's formed like clay. And you can form it around there, and that's what this is right here. That's what this refractory is. So it's very nice to work with. It makes for a really nice complete project when you're finished with it. This area right back here is known as the flash wall, and I wanted to design that very thick, significantly bigger than what's in the 844, because for all intents and purposes we're creating twice the power, if you want to think about it like that. So we need to have a really big, heavy buffer, an area where that flame is going to hit and then reverse direction and then work its way through the rest of the firebox as it's making its way out the front end. And that's put together piece by piece. So it's a little bit of a painstaking process because this is a custom job. This is a custom job. If we had a fleet of these, we would cast brick, and we would make the brick custom, so you would have big, large pieces of brick rather than having to cut and fit each individual piece. So our good friend Paul Gershio, Ted did on the 844, and Jimmy, these guys would be outside, and I would take a brick, and I would measure it, mark it with a Sharpie, and hand it out the door, and they would, and you'd hear them out there cutting brick after brick after brick. So it's a very tedious process, but in the end, you get a really good final product where the bricks are held in there. Now, the reason we do this is because if we have a broken staple, we have to replace that broken staple. What if the broken staple's down here? Well, there's nothing that says that we can keep running the engine with that broken staple. We have to fix it. Well, that means you got to take this all apart to get to the broken staple. So therein lies the rest of the strategy of having a good process where Ted, the fireman, myself, we all keep the expansion and contraction to a minimum so we don't come home after every trip and have to tear all this apart and fix 5 or 6 or 10 or 20 broken staples. Ask me how that happens. So that's why we do it that way. Keep the heat good, take care of everything, do really good work, stay bolts, Jimmy's welding, all of that. It makes for a beautiful job when you're done. And that's what it looks like when you're all done. So this is an area known as the burner deck, and you can't see it because of the lighting here, but this is the front tube sheet and the combustion chamber up in this area here, and this is looking down through the firebox. And once you put a fire in it, it starts to discolor and turn things, kind of blacken things up a little bit. But for the most part, this stuff really holds up well. Another shot of just how tedious this stuff is, because what you want to do, you don't want to have any voids in the brick because that heat transmits through. Look at how thick this thing is. It actually sits up on a little shelf, but that is a very, very thick wall, the Dickens wall of China inside the cab. The cab is so hot because of the heat that's radiating out of this oil conversion. There's no insulation on the exterior surfaces of the fire pan, and how hot is it in there, Ted?
I've seen it as high as 135 in the cab.
Yeah. brutally hot. When you're in the desert in July and August, it's brutal. You gotta love it. Fitting some more of the stuff together, just some more shots of that. And here we are, you can tell we've squirted some oil in there, and we coat it with a special coating that will eventually fire and form a little bit of a glaze and kind of hold everything together for us. This is a whistle connection on the superheater header, and this is the one that we've took out of the locomotive. You can see just years and years of sitting out in the park, and also years and years of being in service. So we take boilerplate, machine everything, and there's a little bronze joint ring that fits down inside of here. And so all of the steam that is needed to blow the whistle comes through that orifice right there. This is the center pin, and we've got Donnie and his bestie Kurt and Austin. And just to give you a size, I wanted them to stand next to this. This is a rough casting that came to us from Western Foundry in Longmont. And we machine it. We apply some bronze lining, just as we did on that other big component I showed you. And we machine it in our big turret lathe. And we've got a liner here, which is hardened steel. It's what we call AR plate. It stands for abrasion resistance. It's just heavy-duty plate. And then we machine all of this. It's all fit together. And this transmits a portion of the weight of the locomotive on the front four wheels. So all of this stuff has to start being fit together, and we've got a big eye bolt because it's the only way you can lift this thing up. I don't know how much that weighs, but it's probably, realistically, probably 700 pounds. And this is just one little piece on the front of the locomotive. And when we took the locomotive apart, this was broken in two pieces. So we knew we had to fix it. Welding it together really isn't going to work because it's an old casting, it's been saturated in oil. Welding something, even if you bake all the oil out of it, you try to weld it, you're never going to get a good job, so just make a new one. And when we made a new one, we tried to estimate why it broke in the first place. And we reinforced it, and we made these areas a little bit larger, and we beefed it up. Something that they would have done if they would have had the opportunity to do that. So this is where it fits on top of, and this is a geared roller rack, and as the locomotive goes into a curve, those front wheels follow the curvature around, but the rest of the locomotive remains in a straight line for that split moment in time. And as it does, those rollers begin to incline upward on that small little rack. It's a rack and pinion, what we call a roller in the rack. The weight of the locomotive on that pin is borne down on a plate that is wearing on these hardened surfaces here that have the same orientation as these surfaces here. That's what it looks like when it's all together. So here's the front four wheels, known as an engine truck. Brand new roller bearings on the inside here, brand new wheels pressed on the axles, all brand new stuff, all new coil springs, brand new leaf springs down here, and we've rebuilt the entire mechanism up front. And when we did that, we made some really significant adjustments when we did the math. And that's what you have to try to get your head around. And when you find an error, you just have to work through the math side of it and double check all your measurements to make sure that you're not missing something, because you're about to alter something. You're going to change the relationship of how these four wheels interact with the rest of the locomotive, because the center of this pin has to be exactly in the same center line on the front where it attaches here, and that's what we're about to do. So we picked this whole big monstrosity up, and we used two big in this instance we used two. We used a 40-ton hook to lift up the back of this, and two big 50-ton screw jacks to lift the entire front engine up in the air. So now we can pull the dolly truck out. We made a special dolly truck, and then we're going to fit this pin up inside, and it gets better. So you've got this giant equalizer and a huge brand new equalizer pin with its hardened liner that prevents wear on this pin that fits up into this, and all this is new too. And we changed this we found it was just a little bit off. So we had to remachine and just do all the work we need to do to reestablish the right relationship on that center pin, and then put everything together. So we've got a crane holding this strap that goes up through a hole in the frame, and it's holding this. This is so big, if this were here, it would span this table onto that table, and it would crush both of those into the ground. This is a tremendously big part of the locomotive. Everything on the locomotive is huge. That pin itself, I would probably set it on the table here, because the combined weight of that and the wrist pin might damage that table. This is big stuff. Well, now you've got this 500, 600, 700 pound center pin. Older locomotives referred to this as a bissel post, and it fits up in its own bushing. We machined this, we took the old bushing out, and we machined where that fits up inside there with a special boring bar. And so just one step after another, after another. Well, now we're finally putting it together. So we slather it up with grease and oil really good, and we set it up in there. I don't know why I jumped ahead here. This is the problem without having the presenter's view. I apologize. But I'll jump back to that in a few moments, and I'll show you the next sequence of events. So these next slides, if I can just jump ahead to those, this is the exhaust nozzle. So this is where the exhaust pressure on the front end goes out of the locomotive. And the work is not done yet. It needs to do one final thing, and that is that jet of exhaust steam, which is still quite hot, and it still has power in it. Remember, the steam locomotives, they got rid of those things. We love them, they're fun to watch, they're cool to listen, but they're not efficient. I mean, goodness sakes, look at the heat that you're wasting. So, one more thing you needed to do, and it goes out and it forms a plume of exhaust steam, which the velocity of the steam moving through there creates a vacuum in the front end of the locomotive. That vacuum is replaced by positive air pressure flowing into those demand air tubes I was talking about, which supplies the combustion air to the fire. So on an oil burning locomotive, this is set up for a coal burner. When you come up to look at these, you'll see that there's nothing down inside here. They're just open holes. Well, when we designed the oil conversion, we essentially modified what the 844 has in it, and it has what's known as a splitter. And you'll see those in a minute. Well, we didn't want, because we weren't 100% sure that this is going to work just the way we want it to, so we want to have the ability to kind of tweak it and adjust it if we have to. So we made everything, instead of making a casting like this, we fabricated it. So we fabricated out of big heavy-duty plate steel. And that's what these are. So each one of these is welded. Now these actually fit down inside a little bit more, but I just set them on there just to kind of give you an illustration. And it looks like a Maltese cross. And each one of these is a very accurately cast little fin, or what we call a splitter. And what the splitter does is it allows a greater range of better performance, whether the locomotive is just kind of drifting along. Now you don't have to use a blower. If you have to use a blower, which is like an artificial draft, that's a waste of steam and water. This allows you the best use of your exhaust pressure throughout a wider range of operations. So that's why that alteration was made there. Now we're going to talk about all the really cool fabrication. We're going to get into Ted's handiwork. Fabricating all the running boards on the side of the locomotive. All of these little intricate welds and pieces, this is all very painstakingly put together by Ted. We draw these big plates in CAD and we send that off to a shop there, Puma Steel in Cheyenne, and they laser or plasma cut these things out, and then we just kind of have a little bit of assembly. We put some more holes in there and actually hand rivet all that stuff together. Okay, here we are. Forgive that, I was trying to organize that stuff. So now we're going to put the locomotive back together. We've got that big giant pin tucked up here. We're holding it with a strap. We've got that giant equalizer which is connecting to this part of the spring rigging. So this connects, and you can't see it behind here, but it connects to that, which transfers the weight down into that centering device on the front engine truck. All the brand new lubrication lines, everything's just nice and really nice. Just really good shape. And then we bring it all down and tie it all together. Now here's another part. This is the part of that exhaust passageway, and we call this a gooseneck. And there's a swivel joint that is upside down the way it's standing there, and I had Jimmy stand by it just to illustrate the size of this thing. You could crawl in here. It's that big. And there's another piece that we had to fabricate that fits over that, and it has some rings. And the cast iron rings help seal that exhaust pressure, because the exhaust from the front engine has to get up to the smokestack so it can contribute that pressure along with the pressure from the rear engine. So that's what makes an articulated sound interesting, is that you've got the exhaust from both engines, and they're not coordinated, they're not synced in any way, they're both working independently. Whereas on the 844, you've got 4 cylinder impulses, 4 exhausts, and they're always the same, because you've got 2 cylinders, and they're all mechanically connected together. 1, 2, 3, 4, 1, 2, bum, 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 bum. Well, on the big boy, you've got that times 2. So that's where you get into the really neat rhythm and the neat sound of an articulated. So the front exhaust has to go through this big component here. And now we've got the 2 mated up, and Austin's up here and I'm running the crane, and we're going to put it together and fit it down into its new home on the front of the engine. And everything to accept it is all new bronze and all new packing. It's all spherical, all lubricated so it all fits together. So when we go around a curve, that is what's moving. So that front engine is following the track, and the boiler is following just a little bit behind it, and the front of the boiler is being pushed over, being influenced by springs known as centering springs, or a centering device. So the front 4 wheels have their own centering device, and it's working and doing its thing in relation to the track structure. It's guiding the front engine. The front engine is moving, and there's 2 centering rods that are pushing on the centering springs and the centering device, and that's what moves the front of the boiler over. It's just an amazing, amazing engineered design. Now we're going to get into putting the boiler back together, because we can't do any of that until we get the front engine back under the rest of the locomotive. We can't make it heavy. We got to keep it as light as possible. So we can't do all of this important work. All this has to wait until the front engine's back under. So now that the front engine's back under, we're going to go to town, and we made this big giant frame so we could form a process known as swedging all of our tubes and flues. So we set up a boiler shop in the West Bay, and we start having a little competition on who can do it faster, because you've got hundreds of these to do. So we take the 100-ton hydraulic press apart, and we modified it to fit in here, and we made a special die to form the end of these tubes. And so we keep bringing these in. We've got them staged outside. We bring them in, pick them up with the crane, set them over here, break them apart, pick them up, inspect them, make sure there's no problems with them, put them inside this frame, secure them with each one of these pieces, swedge it, put it in this pile. These guys pick them up, put them on here, cut them to size, put them in a pile, measure the tube length, get them ready to go, then put them in. One step at a time. Sounds easy, right? So this is what it looks like here. This is the blueprint of what it must look like in order to fit in. So by swedging it, we cold form, we force under hydraulic pressure, we force a die over the end of that tube to reduce the diameter of it, and we increase the thickness of the wall here, and we create the correct relationship here to allow for better water flow around the tubes, and there's an engineered reason why it's designed that way. And here they all are ready to go in. And here they are going in. So as we go through this process, these are the first ones we stuck in. So we've got some stuff down on the bottom so we can walk back and forth. Jimmy, Austin, Ted, Kurt, Troy, everybody's on the outside. And you've got room for a couple guys. Jimmy, you were with me on the inside for a while. And then it gets to a point to where you're running out of room. And these things are pretty heavy. The smaller ones are pretty light. These, let me back up a little bit. These are really heavy. What do we figure each one of those weighed? I'm forgetting some of this stuff. Like 180 pounds, I forget. It's very heavy. So you pick one of them up, and then you get it in with the crane, and you line it up in the inside, and then I pick it up and I put my strap around it, and then I walk along, and then I put it in the other side, and then he's on the other side and he gets it. And then you go to the next one, and you work on this side for a while, and you keep putting them in, and you slowly are boxing yourself in there. And you can see this is known as your tube bundle, and the water is circulating around here when this is in operation. And here's those tube sheet braces, and here's the dry pipe, and this gives you a sense of just how confined it starts to be. And you've got tons and tons of this stuff that you're putting in the locomotive, which is why you can't do it until you've got the front engine in, because you won't be able to physically pick it up. It just takes a big, stronger crane to make it all happen. There's that shot again. Now we're going to talk about our drivers and what we did. We put new tires. Strasbourg worked with us to machine the OD of the tire, or the wheel center, and put new tires on there. And this is the roller bearings after many cleanings and an inspection to make sure that they're in good shape. So this, very difficult to get in there and look at anything. You've got 3 holes, or excuse me, 2 3-inch holes, and there's the lubrication right here. Another view of the rollers. They're just massive. This is the axle. This is the actual bearing race right here. And that's what it looks like once all the stuff is inside there, putting everything together. This is some of Jimmy's handiwork on the lateral motion device spring seat that wears and abrades back and forth as the locomotive's going down the track. And that needed to be built up. Look at those beautiful welds. That's just beautiful welding. So he's building up that part of the driving box, or the cannon box housing, and then very painstakingly grinds and machines it down when you look underneath there. And it really is, it looks really neat when you're underneath there, because it's all dark under there, but you can see those yellow springs and those red lateral motion spring seats. And this is what it looks like before we put the fire pan in. So this is the big frame members for the fire pan. We're looking down on the number 7 driver. All Ted's beautiful handiwork. All those lubrication lines, they have to tuck in very closely right alongside the drivers so they don't work loose and braid up against the rotating wheels. And that's a view from down underneath. You've got these big machine pins, there's bolts that fit in there with big heavy cotter pins on them. Lubrication fittings over here. You've got safety hangers here for this safety hangers and for the equalizer for the springs. Just beautiful work. Nice epoxy paint, real big heavy duty gray paint. And now we're putting the fire pan in. Just some really neat views of how all that works together. This is the front number plate. You can tell that's from my iPhone. I told you I was not an IT person. I couldn't figure out how to make that picture look. I know how to do it now, but I didn't crop it. But that's the front number plate. That in itself is about 45 pounds. Just that bronze casting. Air brake components, putting all these little pieces together. This is Ted's handiwork, and we did the same thing on the 844. For those of you that remember watching some of those presentations, it's the same thing we did on that locomotive. All the air brake work, it's the same type of air brake system. And it's a good thing that we use this, because the heat of that oil conversion would just eat and chew up and spit out the new air brake systems. The new air brakes are made of aluminum components, and they've got little O-rings, and they last for a while, but they just don't hold up like this good old-fashioned 1940s air brake system. Some of the big rods, all the rod work and getting to the point of getting the locomotive all back together again. New eccentric cranks, new crank pins, new rod brasses. This is Ted's handiwork. He goes through and very meticulously cleans up and inspects for cracks and any kind of defect. And we have a rigorous inspection process. And these aren't new components, so they've got a lot of wear on them and a lot of miles on them, so we've got to be really careful when we put them back into service. If there's any nicks or gouges, Ted, with under magnification, uses some very small tools to smooth out anything that could form an area that could present a problem and eventually lead to the component breaking. Valve bushings. All new valve bushings, all new rings. We replaced one of the liners on the locomotive, and all new valve bushings. And this is the process of boring that steam chest before we put that valve bushing in. So you can see the cylinder liner that's been machined. This actually is one of this is the raw casting. And we replaced the cylinder liner in this particular cylinder bore. This is a special boring bar and a special fixture that we made to, forgive me here. This bolts to the cylinder head or the valve chest head, and it allows for adjustment to accurately set this boring bar exactly in the center of that casting so we can bore it and fit those new valve bushings in. The trailing truck, this thing is a monster in itself. And got it all sandblasted. We've took the liners off. We replaced the liners. That's the area, the wear surface that the wheel set goes up and down in. And all that's new and all trammed up real nice, all new spring rigging. That's what you can do when you've got a big overhead crane. You can pick that thing up and tip it over, center, and then lay it back down again. It's a little bit hairy when you do it for the first time, but it's a common practice in rebuild shops. They take GP trucks and do this frequently, SD trucks. It's something that's pretty common. But you flip that over, but it gives you a good sense of just how big it is. Look at how high that thing is standing up in the air. And now we've got it tipped back over, working on the underside of it. And there's Ted and I putting it on its new wheels. So we've got brand new D42 SD70 wheels on the trailing truck. And they're fitted to the original axles, which were still good. And we've got brand new roller bearings, spherical SKF roller bearings on the engine truck and the trailing truck. And they're different between each one, but they're brand new. The ones that we had, who knows, 1 million miles or more. And they probably would have worked for a while, but they need new bearings. So we're lowering this down onto the wheels themselves. And then once we do that, we jack the rest of the engine up in the air and we put the trailing truck in. And there's Donnie. It's kind of a neat shot because it's got all the modern stampings with the D42 locomotive wheel. And we're lowering that back down on itself. We worked out with the city of Cheyenne to use some of the front coupler parts. So we went over one day and used our equipment and we took that front coupler out. You'd never know because all the parts we needed are inside there. And now here we are on these big, nice rebuilt steam joints, and these are spherical joints that allow that flexibility on that front engine. And all that's, the bronze itself is new, and the studs and nuts are new, but these castings are original, and we spherically ground these. Fred, are you here? Did you do that grinding for us?
We did.
Yeah, Fred with B&B Machine, beautiful machine shop, did that spherical work for us. So what we discovered is that we needed to make some slight adjustments in the center line of that sphere just to get the maximum life out of the existing thickness of the material. So we made up for it by compensating the spherical machine surface on this bronze piece here. So little things that you'd never know. In the end, all the relationships are still where they need to be, but it's one of those little engineering calculations you just kind of have to work through when you're putting it all back together again. But this is a great design. This is an American locomotive company. Some of the UP engineering people have their names on the patent as well. It's just a really tried and true design. But this is where your steam flows. This is superheated steam. So this is the hottest steam. This is the hottest areas on the locomotive, is these spherical joints and what we call the steam edges of the valve. And that is what has to be able to, you've got to lubricate it, and it needs to fit together very accurately because it's going to be extremely hot. So when we're operating this locomotive going down the track, you can walk up and touch this thing, but it's over 650 degrees, it's approaching 700 degrees. Well, it's a steam locomotive. It's a superheated, super power steam locomotive, not to be afraid. So if you see flames shooting out of the front of the engine, that's happened twice. That front engine caught fire on 2 different occasions. And you're going to have that. If leaves get down in there, trash or debris. In this instance, we cleaned the locomotive. We used a little bit of mineral spirits, and some of it trickled down in there, and it caught fire. And we're going along, and it's smoking. When we first moved the locomotive and we first ran it, it smokes like crazy. Everything up there is all brand new. It's got oil on it, all that paint, it's smoking and it stinks. Well, then it kind of burns all that stuff off. Most of the paint is just gets burned away. You know, you really can't get the paint that can really withstand it. It says on the package it'll hold up, but let me tell you, it doesn't cut it. So we're going along, and in Austin, he's firing that day. I think, Ted, you were firing when it caught fire one time. And he goes, we got a lot of smoke up here. And then you're thinking, well, we'll just watch it, see what it is. You know, make sure it's not a valve. It could be a valve ring, something you could have a lubrication issue. So you need to stop and investigate it. You know, you don't want to panic every time something's smoking, because lots of things smoke on a steam locomotive. But when it starts smoking a little differently or smelling a little differently, you could have a big problem. Well, next thing you know, there's flames coming out of the side of it. And that's kind of a once in a while kind of occurrence. And so we pull over, and sure enough, this thing's literally on fire. So when you climb down the ladder, you've got a bottle of water with you to put out to extinguish the flame. And sure enough, it was just something that got down in there that caught fire. But it ends up charring the paint on the jacket. That's what it looks like when it's all together. Just beautiful workmanship, piece by piece. This is an elbow support shoe liner plate and all new studs, and it's a precision ground. I think, Fred, you did those for us too. Yep. And the elbow support shoes, all that stuff, it's designed to hold. That thing is so heavy, and because it's a spherical ball, it doesn't have the strength, and it's not designed to hold the weight of that. So it's got this plate that it slides on. So when it goes around a corner, you can see how far those things have moved on either end. And we've got little reference points that we've got in there, the sharpest curves that we've gone around, and we kind of use that. And I can see when it goes around a corner, there's little reference things that I'm looking at. And I know what the curve is anyway. I've gone to look at it. But there's times you might get into a sun kink or something like that. It's interesting to watch that whole big, massive engine move around. And this is the centering device. And these are new here. And these are all machined nice. And there's big, heavy springs. There's a whole set of inner and outer coil springs in here. And that's all it is. That's all it is right there. That's your centering device. And the centering rods are attached to the front engine. And they fit right in here on a small little hardened steel seat. And when that front engine moves, it pushes this entire spring seat inward, and it begins compressing the spring. And as it does, it creates greater and greater and greater force, which begins pushing the front of the boiler over. So the number 5 wheel set becomes like a number 1 wheel set on the 844. So you want to make sure and have the relationships of the centering device and all of that stuff and the dimensions of the centering rods. All that has to be just right So all those relationships work together and you don't end up wearing something out prematurely. And that's the big giant bronze plate. Did you do that, Fred? So we machined the countersinks, and that was a little bit of an expensive casting because we had that piece of bronze cast. It was a little bit expensive. Well, let me see, we're just about done here for our Chama. A few more minutes. And here we are with the beautiful cab. We did just a heck of a lot of work on that cab and replaced a lot of material, putting it all back together again. All new insulation, the nice green paint. We used some of the wood. We wanted to use some of that. Other than having a little burn mark here and there, it was still good enough. But we made a lot of the woodworking that we needed to replace. Beautiful conduit, Troy's beautiful electrical workmanship. We've got 74 volt and a 32 volt panel, the old headlight resistor, modern radio system, and modern cab signal electronics will go right up in here. But other than that, this is 1940s. And here we are in Ogden, Utah. So we're turning the locomotives around, getting ready for this event. And this illustrates the size difference because the track the two locomotives are on are the same level. But look at how the big boy is towering over the 844. It's just, all hyperbole aside, it's a big locomotive. It's huge in every way. When you're sitting up in the cab, when you're going down the track, when you pass other trains, when you go through tunnels, when you go over bridges, when you're negotiating through yard trackage, it's a sense of awesomeness that America would need something like that. The Union Pacific would need a locomotive like this. And they didn't build it so they could get a record or have their name in some trade publication. They built it because they needed it to be that big. But it is built to shoehorn its way through the network. And that's what we did this year. And that's what last year, and that's what we're going to do again this year. So there it is. And that's the size difference between the two. This is one of those shots where very few photographers are present. And I apologize for that. That's not our intention. We would love for everyone to be able to get a good photograph like this. But as it worked out, we had to be tucked away down at CP 988 Riverdale as we made this turn move. So in the busy course of our day, we've got both main lines tied up. Don't think the dispatcher's not calling. But my ace in the hole is I have the superintendent in the cab with me. And we talked about, because we had a few different variations on what we were going to do, and he made a recommendation that would involve tying up the main line. And I said, "Sir, would you mind coming with me? Come on up and ride." My strategy was that you call the dispatcher for me. And so he's calling the dispatcher while we've got both main lines tied up. But that's just one more accolade to the Harriman Dispatch Center. And Keith Miller, are you here? He may have stepped out. He's one of our passenger network ops guys with the Harriman. We can't do this without them. They are giving us the clear signals. They're lining up our routes. They're taking care of our crews. They're doing everything to make this work. So what an honor it is for us to take these locomotives around the big network and have everybody cooperating with this and working with us as this great big yellow team making this stuff work. And with that, I thank everyone for coming, and we sincerely appreciate your support. And for those of you that aren't a member of Facebook, we have a Facebook page. We call that Steam Club. And if you're interested, check it out. We announce all the latest information that we have. We're going to be releasing our trip, the upcoming trip in August pretty soon. We've just got a few other little logistical things to work through, but we'll have that information out soon. We'll also have some more updates. We've been busy with a lot of things, so we haven't had too many updates lately. So thank you very much, everybody. I think we're running a little bit short on time, so I'd like to introduce our next presenter. If we could flip our lights on. And thank you, everyone.